Alright, section 13.4 is on two new types of identities. One is called a double angle identity, and the other type of identity is called a half angle identity. So the main goal for this section is just learn how to use those, what they mean, and how to apply them to find exact trig values. So we'll show you those identities and then do a couple problems with those. Okay, so these are the double angle identities, and if you're wondering where they come from, these are kind of based on the prior section. So in the prior section we talked about the sum and difference identities. I'll just show you where sine and cosine come from. So you may remember from the last section, this was the identity for sine for adding angles. It turned out to be sine of the first cosine of the second plus sine of the second cosine of the first. So now let's apply that to sine of 2 theta. And sine of 2 theta can be written like this. It can be written as theta plus theta, because theta plus theta is 2 theta. Well, if we follow this pattern right here, we're going to get sine of theta cosine of theta plus sine of theta cosine of theta. And if you have a sine theta cosine theta, you add another one to it, you end up with 2 of them. So that's where that identity actually comes from. The same reasoning could be applied to cosine. So let me show you one of those. Whoops, let me clear those off. Here's the identity for cosine addition. So again, we could write 2 theta as theta plus theta, and you might remember the identity from last section. It went cosine of the first cosine of the second minus sine of the first sine of the second. But obviously in this case the first and the second angles are identical. So what's another way of saying cosine times cosine? That would be cosine squared, and another way of saying sine times sine would be sine squared. So that's where that first version comes from. Why are there 3 different versions for cosine? Because we have identities for sine squared and cosine squared, which are based on this one right here. So because sine squared plus cosine squared equals 1, you could rewrite, let's say this identity right here, you could replace this one with 1 minus sine squared, because based on this identity, if I subtracted sine squared from both sides, cosine squared does equal 1 minus sine squared. So if I replace this thing with 1 minus sine squared, and then I have another, this minus sine squared right there, minus sine squared minus another sine squared would be this one, minus 2 sine squared. And you could use the same reasoning to get this second one. So basically with the cosine of 2 theta, you have several different identities you could use that will give you the same answer. And as we'll see, some of them tend to be more useful than others in certain cases. Alright, so this one says find the exact value of sine 2 theta if sine of theta is 2 over 3 and theta is between 0 and 90, which means we're in the we're in the first quadrant, because 0 to 90 is, here's 0 and here's 90. So first of all, sine of 2 theta, that means we're going to be in a different quadrant, because theta is in the first quadrant, but 2 theta is going to double that. So we don't actually know, like if, for example, if theta were 10 degrees and you doubled it, you would still be in the first quadrant. So we're going to have to account for that momentarily. But here's our formula for the sine double angle, and all we need to do is plug in what we're given. So we're given, we are given sine, so I can plug that in right here. So 2 times sine of theta is 2/3. Problem is we don't know cosine, but we do have an identity that allows us to find cosine once we know sine, and here's that identity. Okay, that identity that we've seen a bunch is sine squared plus cosine squared is equal to 1. Okay, we know that sine is equal to 2/3, so let's plug in 2/3 right here and square it. And then when we solve this, 2/3 squared is 4/9. And so we're going to need to subtract the 4/9 from both sides. 1 is the same thing as 9 over 9. So 9 over 9 minus 4 over 9 would be 5 over 9, and that's equal to cosine squared. We'll square root both sides and put a plus or minus in front of it. And then that simplifies down to cosine equaling the square root of 5 over the square root of 9, and the square root of 9 is 3. Now again, we put a plus or minus in front of that. How do we know which is which? Well, they tell us up here that cosine is in, or theta is in the first quadrant. It's between 0 and 90. And if you remember this acronym, all students take calculus, all things are positive in the first quadrant. So that means the cosine will be positive root 3, or positive root 5 over 3. So let's plug that in now that we found cosines. We have 2 times 2/3 times the thing we just found cosine to equal. And 2 times 2 would be 4, so we have 4 over 3 times root 5 over 3. And that's going to equal 4 root 5 over 9. And that right there is actually the value of this. It's the value of sine 2 theta. So let me show you how to check that on a calculator. We can actually find what this angle is right here. You may remember from chapter 12, if we want to cancel out the sine, we can take the inverse sine. So let's figure out what angle it actually is that has a sine of 2 over 3. So first let's make sure we're in degree mode, and we are. So second inverse, our second sine of 2 over 3. Oops, and that's going to give us the angle that has a sine of 2/3. That's what inverse sine does. So the angle that does that is a 41.8 degrees. And remember, we're dealing with 2 theta. We're dealing with double that angle. So here's what we can do. Let's double the angle we just found, which means 83 degrees. And let's find the sine of that angle right there and check it with what we ended up with. So we get 0.9938, and our answer is 4 radical 5 over 9. So let's double check that that's actually the same number, because one of them is in radical form, one of them is in decimal form. But hopefully we'll get the same thing, and we do. So that's a nice way that we can check. Basically, we just found what angle had that sine, we doubled it, took the sine of that, and we got the same answer both ways. So it's a nice way to check. Alright, let's do a couple more here. Just trying to see which one. These are both kind of the same thing. I think 4 is a little bit more challenging, so let's look at number 4 instead of number 1. So first of all, they're telling us that theta is between 540 and 630, so we have to figure out where that is. So if we go all the way around, that's 360 degrees. Okay, and then remember, each one of these segments right here is 90, so let's figure out where 540 would put us. So we're at 360 right here so far. If we go another 90 on top of 360, 90 plus 360 is 450, so we're not there yet. If we go another 90, now that's 540. And if we go another 90, that's 630. So that means we're in this third quadrant right here. And in the third quadrant, only tangent is positive. So that makes sense. They're telling us cosine is negative, and we would expect that based on the fact that we're in the third quadrant. Okay, the only thing is we don't know where 2 theta is going to be. We know where theta is in the third quadrant. 2 theta could be in any number of places. So we're going to have to figure that out. But you don't actually, I should clarify, you don't have to figure it out if you just use this formula right here, because this formula will naturally take care of whether it's positive or negative. Okay, so let's find the sine of 2 theta using this formula again. 2 sine cosine. We know cosine because they told us right here, so let's plug that in. Cosine is equal to negative 3 over 5. We don't know sine, but we can find it by using this identity right here. And that's usually what you have to do. They're going to give you just one of them. So you use this identity to find the one you don't know. So negative 3/5 squared is going to be 9 over 25. And then we're going to isolate the sine by subtracting 9 over 25 from both sides. Okay, and actually this a little bit of an overkill, because I'll show you why in just a sec. You might already recognize what kind of triangle this is going to be. 25 over 25 is the same as 1. So if we do 25 over 25 minus 9 over 25, we get 16 over 25. That's equal to sine squared. And we can solve for sine by rooting both sides. So that means sine is equal to plus or minus, and it's going to be minus this time because we said right here we're in the third quadrant. It's going to be minus the square root of 16 is 4, and the square root of 25 is 5. The reason I said that's a little bit of an overkill is you might recognize that the most famous of all right triangles, or Pythagorean triangles, is a 3, 4, 5 triangle. And based on the fact that this was 3 and that was 5, if you use the Pythagorean theorem, that would have to have been 4. But you know, if you don't notice that, or you don't remember that, then that would be the way to do it. So let's figure out what this is going to be now. So cosine is still negative 3 over 5. Sine we just found is negative 4 over 5. So that's going to be 2 times negative is positive. 4 times 3 is 12. 5 times 5 is 25. And then 2 times 12 is going to be 24 over 25. Now you might say, well, how is that positive? Because theta is in the third quadrant. Remember, we're dealing here with 2 theta. So 2 theta, if we have some angle in the third quadrant, we double it. I'm just trying to think of an example here. Let's say this was like 200 degrees. Let's say 200 degrees would be in the third quadrant. If you double 200, you would get 400, and 400 puts you all the way around 360, and then another 40 into the first quadrant where sine is positive. So that still makes sense that we would have a positive answer as our final result. Okay, let's do both of these. So it says we haven't done ones with cosine and tangent yet. It says find the exact value if sine is 2 over 3 and theta is between 0 and 90, which again means we're in the first quadrant. But we don't know where 2 theta is going to put us. 2 theta could put us either in the first quadrant or in the second quadrant. So before we solve either of these, if you look at these formulas right here, we're being asked for cosine and we're being asked for tangent. So let's find, they're giving us sine of theta. Let's find cosine of theta and tangent of theta, because we're going to have to use those in both of our identities. So here's our first step, is to find. They're giving us sine. We're looking for cosine, because you may remember from the previous 2 problems that we've had to do that twice now. And actually, I think we did this exact one before. They told us, just to recall, yep, they told us right here on this other problem that sine was 2/3, and when we did that, we got cosine equaling radical 5 over 3. So let's save ourselves a step there and just find out what cosine, fill in what cosine is right here. It's radical 5 over 3. And now that we know sine and we know cosine, we can find tangent, because tangent is equal to sine over cosine. And sine in this case is 2/3, and cosine is radical 5 over 3. So those will cancel each other out. Now when you simplify, you're going to get 2 over radical 5. And when we rationalize both the top and the bottom, we would get 2 radical 5 over 5. That's equal to the tangent. So we have cosine, we have tangent. Now we can start to use that. So it says find cosine of 2 theta. Well, again, remember I told you before that there's 3 different versions of cosine. Which one do you want to use? You can actually use any of them, but I would suggest the easiest one to use is the one that only has sines in it. And the reason that one is easiest is because they started out by giving us only sine. Okay, obviously we ended up finding cosine, but if you wanted to save time, you could just use the one with sine. So this is one of the 3 versions of cosine, and we know what sine is. We know that sine is 2 over 3, so we're going to do 2 over 3 squared. Okay, 1 minus 2 times 2 over 3 squared is 4/9. So that's going to be 1 minus 2 times 4/9 is 8/9, and 1 minus 8/9 would just be 1/9. So that's what cosine of 2 theta is equal to. Okay, the tangent is equal to this right here. There's only one identity for that. So let's just plug that in. So tangent of 2 theta is 2 times tangent of theta over 1 minus tan squared of theta. We found the tangent of theta up here. Just to recall, tangent of theta, we plugged in our sine and cosine, and we had that 2 radical 5 over 5. So let's just use that. So this is going to be 2 times 2 radical 5 over 5 over 1 minus 2 radical 5 over 5, the whole thing squared. Alright, so the top one is going to be 2 times 2 radical 5. The 2 times 2 will become 4 radical 5 over 5. I'm just writing that on one line so we can see what we're dealing with on the bottom a little bit easier. And then this thing right here, when you square this, when you square that, 2 squared is 4. Radical 5 squared is just 5, so that's going to be 4 times 5, and then 5 squared on the bottom is 25. So 4 times 5, that's going to be equal to 20. And then remember, 1 is equal to 25 over 25. So let's just clean this up a little bit. So the top is still 4 radical 5 over 5. The bottom, this right here, is the same thing as 25 over 25. So 25 over 25 minus 20 over 25 is 4 over 5. 25 minus 20 is, nope, sorry, that's a mistake. It's not 4 over 5, I'm not sure where that came from. 25 minus 20 is 5, and then that's going to be 5 over 25, which equals 1 over 5. So, yeah, obviously you have to be careful, more careful than I was with these simplifications. So dividing by a fraction is like multiplying by the reciprocal. So that thing right there, 4 radical 5 over 5 times the reciprocal of that times the reciprocal of 1 over 5 is 5 over 1. So those will cancel, and we'll just be left with 4 radical 5 as our answer for tangent of 2 theta. So that's what it turns out to be. Alright, the last thing I want to show you here are the half angle identities, and there are proofs for where these come from. They're again based on the kind of the double angle identities, but let's see if I can yeah, so here's an example where this comes from. It's based on the cosine 2 theta double identity. So I'll just show you the one of these right here. So remember, cosine of 2 theta is equal to it's equal to this. One of the versions of it is equal to 2 cos squared minus 1. Okay, let's actually solve that for cosine. So this, let me fix this a little bit. This is equal to 2 times the cosine squared of theta. If we solve this for cosine, we would do this. We would add 1 to both sides. We have 2 cosine of 2 theta plus 1 is equal to 2 cos squared theta. Let's divide both of these by 2. So we're going to have this. We will have, move it off to the side a little bit here. It will have, and I'll reverse this. I'm just changing the order of this right here. So 1 plus cosine of 2 theta over 2, and that's equal now to, these things have canceled, so it's equal to its cos squared of theta. And how do you solve for cos? If it's cos squared, you would square root both sides, and in front of the square root you put a plus or minus. So this thing, square root of cos squared equals cos of theta. Now you might look at this and say, how does that look like, for example, this identity? Well, you can see you have the plus or minus square root part. So let me circle that so you can see it. So we have the plus or minus, we have the plus or minus, we have the 1 over 2 part, and there's the 1 over 2 part. We have this radical part here and this radical part here. The only difference is this is cosine of theta, that's cosine of 2 theta, this is cosine of half theta, this is cosine of regular theta. So that identity, the half angle identity, comes from that process that we just did. The only difference is that they've cut these angles in half. So you can see what's the relation between theta and half of theta. Well, this one is half of theta. And similarly, this one right here is half of 2 theta. So there's still a relationship between them. The only difference is that when we do these problems, we're not going to have 2 thetas in there. We're going to have just regular thetas. Yeah, you don't have to know that proof or anything. I just wanted to show you that there is these identities don't just come from nowhere. They come from rearranging previous identities that we already know. Alright, this one says find the exact value of cosine theta over 2 if they give us that sign. It's a little bit hard to see, but that's a negative right there. And theta is in the 3rd quadrant, so that's important because that's going to tell us whether it's positive or negative. Okay, so cosine of theta over 2 is this identity right here. Okay, and then we'll have to figure out this plus or minus part at the end, and I'll show you how to do that. Actually, we can do that right now. Theta is in the 3rd quadrant. The 3rd quadrant starts at 180 degrees and it ends at 270 degrees. That means theta is between these two numbers right here. Okay, so how do we decide whether to use plus or minus right here? Here's how we decide. We need to find out where theta over 2 is. So if theta is in between these and theta over 2, we would get that by just dividing by 2. 180 divided by 2 is 90. This is theta over 2, and then 270 divided by 2 is 135. So that means our half of our angle, theta over 2, means half of theta. That's how you take half of something, you divide it by 2. our half angle is between 90 and 135, and here's 90 and here's 135. So this right here is in the second quadrant, which means in the second quadrant, we're trying to find cosine of theta over 2. In the second quadrant, only sine is positive, cosine is negative, so we're going to take this negative right here as our value. Okay, the other thing too is, if you notice in the formula, we need to know what cosine is. We can't use sine in this formula, we need to know cosine. So this right here, we actually figured it out on a previous problem by using this identity right here. Yeah, if you plug in -4/5 there, you would end up with cosine of theta equaling -3/5. And we've done that in a previous problem, so we'll skip that step. Okay, now we're ready to use our formula. So the formula again is this one right here. We knew that it was negative. I'm putting a negative in front. We knew it was negative because we found out that theta over 2 is in 90 to 135. It's in quadrant 2, and cosine is negative there. Okay, then we're going to have 1 plus the cosine of theta, but we just found that. The cosine of theta is -3/5, and that whole thing is over 2. So 1 plus -3/5, that's going to equal 2/5, and then we have 2/5 over 2. So dividing by 2 is like multiplying by the reciprocal of 2, which is 1 over 2. Those will cancel, and we're left with negative radical 1/5. And then the only thing we want to do after this is just clean this up a little bit. So remember that when you have the radical of a fraction, you can take the radical of both of them separately, and then let's rationalize this right here. And we will end up with negative radical 5 over 5, and that should be our answer right there. Let me show you how you would be able to check that, by the way. So here's how you could check it. We kind of do what we did last time. We know that the sine is -4/5, so let's take the inverse sine of that just to see what angle that is. And we know that the angle should be in the third quadrant, so that's a way to tell. So -4/5, and hopefully we'll get a third quadrant angle here. Actually, we don't. So this is what's called the reference angle. We talked about this in Chapter 12. The reference angle is 53, so you would have to add that to 180 to get your actual answer. I don't want to confuse anyone here, so we'll actually save that in terms of checking. We'll save it for another problem, because the explanation might be a little bit too confusing. But we did the process correctly, so even if we don't check, it's not a huge deal. We still got the right answer using that process. Okay, slightly different example here. It's still the half angle, and one of the ways you can tell that this is a half angle is it's ending in 0.5. Usually, if an angle ends in 0.5, that usually means you got it by taking half of something. So this right here, this is our half angle. This is theta over 2. We took some angle, we cut it in half, and we got 67.5 degrees. This is a little bit easier than the other problem, because we don't have to guess what theta is. We can solve for it directly. We can multiply both sides by 2 and multiply this by 2. This number times 2 is 135 degrees. So now we know exactly where we are. We're in the second quadrant, where cosine is negative, because it's all students take calculus, and 135 is in the quadrant where sine is positive. So now let's plug in our half angle formula right here. And in terms of deciding whether it's plus or minus, this plus or minus in front is based on what theta over 2 is, what the half angle is. 67.5, that's in the first quadrant. And in the first quadrant, cosine is positive. So I'm going to take the positive right there. Okay, and then underneath the square root, we have the rest of it. We have 1 plus cosine of theta. And we found out that theta is 135, so it's going to be 1 plus cosine of 135 over 2. Okay, now we can do the rest. So 1 plus, what is cosine of 135? Well, remember, here's 135 right here. It's this one. So we need to find the reference angle. And the reference angle is the angle that takes you down to 180. And for 135, the angle that takes you to 180 would be 45 degrees. However, it's negative. So this is the same thing as the negative of cosine of 45. Why is it negative? Because we're in the third quadrant. Why is it cosine of 45? Because 45 is the reference angle for that. Alright, so let's finish this problem. So I'm just going to leave out this positive because we know it's positive right now. The cosine of 45 is radical 2 over 2, but again it's negative because it's actually the cosine of 135. We're in the quadrant that gives us 135. So there's a couple ways you could simplify this, and this is usually where people make mistakes. We could just change 1 into 2 over 2. So that's a common denominator with this one now. So we will have 2 minus radical 2, the whole thing over 2. The minus radical 2 is right here, and there's that 2. So 2 plus negative radical 2, or 2 minus radical 2. And then let's keep simplifying this. So we have 2 minus radical 2 over 2, and then we're dividing by this number, which is like multiplying by its reciprocal. So this is going to simplify to this. It's going to be 2 minus radical 2 over 4, and then we can take the radical of both the top and the bottom, and the square root of 4 is equal to, it's just equal to 2. So even though this final answer looks kind of messy, you have a radical under another radical, that is actually the answer. That's the exact answer. So here's an easy way to check. I said we'd come back to checking. We're going to take this number, plug it into a calculator, and we should get the exact same number as this plugged into a calculator. Okay, this one is not hard to check. So let's do the cosine of 67.5, and here's the key thing, the exact value. When you type in cosine of 67.5, it's not going to be exact. They're going to give you a big long decimal. Okay, that's 0.3826. That's not the exact value though. The answer that we found down here is the exact value. So let's double check that. So we have the square root of 2 minus the square root again of 2, and then we were supposed to divide that by 2, and you can see we get 0.3826, which is what we got by just plugging in cosine 67.5. So that one is not hard to check, and it's a good idea to check in that case. Okay, let's do maybe one more of these. We'll do the sine of 135. Actually, we'll do the cosine of 7 pi over 8. So 7 pi over 8, the first, probably the easiest thing to do would be to change that into degrees, because degrees tend to be more intuitive for people. So if you remember, the way that we change radians to degrees is there's a pi on top, so I need a pi on the bottom to cancel. And there's 180 degrees in every pi radian, so those will cancel. 4 goes into that twice, and it goes into that 45 times. So 7 times 45 is 315, and when you divide that by 2, you end up with 157.5 degrees. So that's what this is asking us. This is asking us for the cosine of 157.5 degrees. And remember, this right here is theta over 2. So what was theta? Well, we kind of figured it out right here. Theta must have been 315 degrees. You could just take that and double it. So that's going to help us because we know that 315 degrees is right here. Okay, so that is theta, and theta is in quadrant 4, where only cosine is positive. And where is 157.5? 157.5 is in quadrant 2, where only sine is positive. Okay, so that gives us some more information. So now when we're looking at, we're being asked to find the cosine, so that means this formula right here. The plus or minus here is determined by where theta over 2 is, and theta over 2, we said, is in this quadrant. It's where sine is positive, but cosine is negative. So we're going to take the negative radical, and then we're going to have our cosine formula is 1 plus cosine, so 1 plus cosine of theta. What is theta? We found it right here. Theta is 315 degrees. Okay. Now here's the thing, we don't directly know 315, but we do know the reference angle. It's what takes us up to 360, and 360 minus 315 is 45, so kind of just like it was before. The only difference is this time cosine, we're in the fourth quadrant where cosine is positive. So even though the negative outside, the negative is for theta over 2 for the half angle, but this angle right here is not negative because it's in the quadrant where cosine is positive. So remember, this is the same as the cosine of its reference angle. What's the cosine of 45? It's radical 2 over 2. And now we have a problem very similar to what we had before. So here's the rest of the simplification. From this point, you change 1 into 2 over 2 and make a common denominator. And then from there, you can actually, I simplified a little bit different than last time. But what you can actually do here is, you have this negative right here. Dividing by 2 again is like multiplying by 1 over 2. So the 2 times this thing will be 2 over 4. And all I did was split it there. And you end up with this answer here, which is almost the same as what we had on the other one, just with a positive instead of a negative. Alright, last thing I want to show you is how to verify an identity. So we can use these formulas to, let me just pull up the formula so we can have it. We can use this formula right here, the cosine formula, to use to verify things. And actually, we're using a double angle right here. So remember, cosine of 2 theta has 3 versions. It has cos squared minus sine squared. It has 2 cosine squared minus 1 as another version, and it has 1 minus 2 sine squared. These are double angle identities, back what we did at the start instead of half angles. Alright, so the question is, and actually we also have a sine double angle there as well. The question is where to start, and you may remember from earlier that in an earlier section we said the rule is to start with the more complicated side. They both look pretty complicated, but usually you want to start with the side that has a double angle on it. That's generally the more complicated side. So what should we do? We're trying to change stuff into cotangent. It's not obvious how we would do that, but let's just start changing things and see where it leads us. So first of all, the sine, we don't have a choice for this. The only double angle for sine is plus 2 sine cosine. And we have a number of choices for this. I'm not sure which one to use, but remember, cotangent is cosine over sine. So I might want to use the version that has both sines and cosines in it, because I know that cotangent has both. And the version that has both of them in it is this one right here. So I'm just going to change cos 2 theta into this. Again, we're not entirely sure where this is going to lead, but hopefully we'll be able to make some progress. Alright, so what should we do at this point? Well, it's not entirely clear, but let's do this. Let's change 1 plus 2 sine cosine on the bottom. Let's think about this. How might we be able to change things to give us a good result? You know, what we can do at this point is if it's not clear where to go, you can always use the strategy of meeting in the middle. So it's not very clear where to go. We're not sure how to change the other side. So let's box that off and let's start working on the right side. So this one right here, we know that we're supposed to end up with sines and cosines. So let's change cotan into what it is. Cotan is cosine over sine. So that's the top. And then this one would be cosine over sine plus 1. Okay, now we have fractions, so we can change this into a common denominator. 1 is the same as sine over sine. And down here the same thing. 1 is the same as sine over sine. Okay, so now if we add these together, we would have cosine minus sine on the top, cosine minus sine over sine. And then I'll use a different color so we can see this. This one right here, we have cosine plus sine over a common denominator of sine. So cosine plus sine over sine. Now we have a fraction divided by another fraction, so the saying for that is copy dot flop. We're going to copy this first one. We're going to change that to multiplication with the dot, and then we will flip this around. So we'll end up with sine over cosine plus sine. Okay, now notice these will cancel, and when we simplify this a little bit more, we're going to be left with this. We'll be left with cosine minus sine over cosine plus sine. Okay, so how can we, so if we look back at what we're trying to get here, we're trying to get this. How can we change it? And you might notice that the top right here almost looks like this one, except both of them are being squared. So you may or may not see it, but this right here is actually a difference of squares. It's the same as cosine plus sine times cosine minus sine. So what we can do here is we can use something called the conjugate. and I'm going to multiply the top by its conjugate. Normally we multiply the bottom. We won't do that in this case because we're trying to get a difference of squares to show up on the top instead. So that's why it was a good idea to kind of have them meet in the middle, because we wouldn't have known how to do this, or that we needed to do this unless we had seen this thing right here. So again, why are we multiplying by the conjugate? Because I see that I have a difference of squares up on the top left in red, and the only way to produce that is by using the conjugate. So let's simplify this a little bit. So we'll have, when we FOIL out the top, we're going to have cosine times cosine is cosine squared, minus sine times plus sine is minus sine squared. The outside and inside terms will cancel. You have cosine times sine, positive, cosine times negative sine, negative. Those will actually cancel each other out. And then the bottom is going to be cosine times cosine, which is cos squared, sine times sine, which is sine squared, and then the inside and outside terms will be this. Inside terms will be sine cosine, and the other ones will be sine cosine. So you have sine cosine plus another sine cosine. That's going to actually equal 2 cosine, or 2 sine cosine. Okay, and actually we're almost there. So this right here is an identity that's equal to 1. So if you look at this now, let me get rid of this. We have cosine squared minus sine squared over 1 plus 2 sine cosine. And that is exactly what we have right here in red. So we use the strategy of getting them to meet in the middle as our go-to. Let's do one last one. Verify that 4 cos squared minus sine squared 2x equals this thing right here. Well, again, here's a double angle. So usually the strategy is to, I'll use theta instead of x. Usually the strategy is to immediately change the double angle to whatever its identity is. So let's try that. So we have 4 cos squared. I'm using thetas instead of x just to not throw anyone off. Okay, so the sine of 2 theta is equal to this, and I'm going to put that in parentheses because we're squaring it. Okay, and I've obviously started with the left side because the left side is more complicated than the right side, so let's keep simplifying here. When we square this, square each thing, we'll have 2 squared is 4, sine squared is sine squared, and cosine squared is cosine squared. Okay, remember we're trying to change it into something that only has cosines in it. So what can we do here? Well, we can think of this identity. What's an identity that would enable us to get this thing to have only cosines in it? And of course it's this identity that we've used very often. So let's solve this for sine squared. Okay, so sine squared is equal to 1 minus cosine squared. So I'm going to make that replacement. Why am I doing that? Because I'm looking at what I'm trying to prove. I'm trying to prove something that only has cosines in it. So it makes sense to get rid of the sines by replacing with cosines. So that's what we have right there. And then let's just distribute this. So we'd have cosine squared being distributed to both of those. And when we do that, we're going to have cosine squared minus this right here becomes cosine to the 4th. That's a good sign because that's what we want. We want something with cosine to the 4th. And let's just distribute this now. So we have 4 cosine squared minus 4 cosine squared. The negative 4 times the negative becomes a positive right here. And then these cancel each other out. We're just left with 4 cosine to the 4th. And that's exactly what we're trying to prove right here. Okay, so that is section 13.4 on double angle and half angle identities. It's certainly a lot, but the more that you practice with it, the better it will become.